Okay, this is the third page of notes for week 11. And we're talking about antiderivatives, also known as indefinite integrals. And there's a number of formulas throughout these pages, and what I've done within these notes pages is intersperse the formulas throughout, right before, soon before a problem or an example where we need to use them. So I'll collect all the formulas on a separate page and upload that to Blackboard with the notes pages. And as you do the homework 11.1, it would be helpful to have that formula list as well as these notes pages to look through for similar type example problems. So here's a formula, and we can confirm that formula by doing the derivative of the right-hand side. So the derivative of the natural log of the absolute value of x plus k. K is a constant as well as c being a constant. This was a formula. This was equal to 1 over x plus k times the derivative of x plus k. That derivative is going to be 1 because the derivative of x is 1 and k is a constant, plus the derivative of c is also a constant, so that's a 0. So this is 1 over x plus k, which is just showing that the derivative of the right-hand side over here is the integrand, which is what an indefinite integral means. I forgot the dx there. See right here. So that indefinite integration symbol is always a sandwich, so to speak, with this indefinite integral symbol, and this should be the dx there on the other side. So that's a formula that comes up from time to time. The next one's actually super important, and it looks a little worse than it is, I would say. With all the n's and things floating around, it looks kind of daunting. But this is the backwards version of the power rule for derivatives. The biggest rule that we always use, the power rule, where we're taking the derivative, we reduce the power by 1. But we're going backwards now when we're doing antiderivatives or indefinite integrals. So we have a power of n, we have to increase that by 1. When we take an antiderivative or an indefinite integral, we have to increase the power by 1. It's backwards to before. We also have to put a 1 over n plus 1 out in front. And we did one like that on the first page of this week 11 packet. We didn't do it with the formula, we just kind of reasoned through it. We had to put a 1/2 in front of an x, and you can go back and check that out. But I want to do some just little examples of this formula here. Just this one doesn't have really a name, but it's the backwards power rule, so it might be called the reverse power rule. And it's really super duper important. So here's a few little examples of it. First, a real basic one. Say you got x to the 5th, the indefinite integral of x to the 5th. So that's 1/6. That's the 1 over n plus 1 part. X to the 6th plus c. And the check of that, like always checking indefinite integral statement like this, is to evaluate the derivative of this side. So that's going to be 1/6 times 6 will be 1 x to the 5th plus 0, which is x to the 5th. And that's the integrand. So that's good. Okay, so I want to do another example of this reverse power rule. And One thing where the rule still applies, but it gets a little bit harder to apply is if you have a negative number for the exponent. Maybe just don't try to overthink it, just follow the formula. Add 1 to the exponent. So I'm going to actually write it out as negative 3 plus 1 x to the negative 3 plus 1 plus c. Negative 3 plus 1 is negative 2. So 1 over negative 2 x to the negative 2. When you increase a negative number by 1, and this formula is to increase by 1, add 1, it gets closer to 0. Negative 3 plus 1 is negative 2, not negative 4. And I fully realize all you guys know that, but sometimes when you're doing this, especially do so many that are positive, it's 5 becomes 6, 3 would become 4, and so forth. But negative 3, when you add 1, becomes negative 2. So, okay. And then one other situation where we can use this rule, but it's a little bit harder than when it's an integer. 5 and negative 3 are both integers. Positive is easiest, negative is a little bit of trouble. But this can be a dreaded fraction, like 1/4. So n is equal to 1/4. And we know that part of this is going to be n plus 1, so that's 1/4 plus 1. 1/4 plus 4/4 is 5/4. Okay. So this would be 1 over n plus 1 is 1 over 5/4 x to the 5/4. So you see how it's the same. Go back to the 1 over 6 one. So it's 1 over n plus 1 x to the n plus 1. That's the same thing here. So don't be too thrown off by fractions. It's 1 over n plus 1, 1 over 5/4 times x to the 5/4. Now the 1 over 5/4 we can clean up, keep change flip, keep the 1 times 4/5 x to the 5/4 plus c. Now I'm going to leave it to you, but take the derivative of that, even just mentally, or write it off to the side, and make sure you get back to x to the 1/4. Okay, now number 4 down here, this problem to evaluate the indefinite integral is going to use those two formulas we just talked about, as well as this property. So this property of integrals, much like for derivatives, when you take the derivative of f of x plus g of x, you take the derivative of f plus the derivative of g. And integrals have that same kind of property, both with plus and minus. So when the integrand is f of x plus or minus g of x, we evaluate each integral separately and add or subtract, respectively, to get the indefinite integral. And even when your integral has two terms like this, you don't need plus a c for each one of them, but the indefinite integral will have 1 plus c at the end. Okay, so the property tells us we can do this. We basically deal with them each on their own terms separately. So the integral of x to the 1/2 dx plus the integral of 1 over x plus 7 dx. The integral of x to the 1/2 is much like what we did up here a minute ago with x to the 1/4. So I'm going to kind of do scratch work off to the side here. For that part of this problem, n is equal to 1/2. And we know we're concerned with n plus 1, which is 1/2 plus 2 over 2, which is 3/2. So let's go ahead and apply the rule, keeping this in mind. N plus 1 is 3/2. So the rule, the formula, is here, 1 over n plus 1, so that will be 1 over n plus 1 is 3/2, 1/2 plus 1, x to the n plus 1 is x to the 3/2, plus, now this integral is the very first formula, the tippy top of the page. The integral based on the ln, the integral of 1 over x plus k is the natural log of x plus k, in this case 7, an absolute value, and then 1 plus c at the end. We don't need separate plus c's. We wouldn't really want to write separate plus c's. We could write a plus c1 and a plus c2, but then since the value of c, if you remember, is an arbitrary constant, it can be any real number. Were we to write plus c1 and plus c2, we could just kind of say, well, since c1 can be any number, it's c2 as well, let's just replace that sum with one parameter c. Oops, I didn't quite finish that. Let's see. Just gonna, because we gotta clean this up just a bit. Now 1 over 3/2 is 2/3. X to the 3/2 plus the natural log of x plus 7 in absolute value plus c. So that's it. Now, I do want to mention here, because a lot of you are probably noticing when you look at, what would it be, up here, and this is true, this is how it works, but sometimes, I don't know what it is exactly, but people don't take the time to work through this right here. So what am I talking about? Well, you see how if it's 1/4 and you add 1 to 1/4, you get 5/4. Then it will turn out to be 4/5, x to the 5/4. So the reciprocal in front times x to the power. Sometimes I think people just try to memorize it that way, but then the memorization catches them out, and they get some different things wrong about that. So you see this one work, this first term, that works the same way. 1/2, add 1, that's 3/2, and then it's 2/3 x to the 3/2. But it comes from the same formula, the reverse power rule, as if it were the integral of x to the 5th. So it is a pattern, just how it works when you have a fractional exponent. You pick up the reciprocal of the exponent out in front. But I would just caution you, if you do that kind of shortcut, sometimes it leads people astray. Just be careful. Alrighty.